Well, good morning and welcome to our last RMHAM University for this year. My name is Willem, AC0KQ, and our presenter today is Mike Langhenry that's going to talk about lightning protection and grounding. So before we get to that, just a few pointers for the folks in the room. Bathrooms are down the halls, up the stairs before you go through the doors, and the bathrooms are right above us. You can get back into this room from there. If you go through the doors, make sure that you take one of those little cards with you so that you can get back through from the lobby into this part of the building. The other thing I always have to remind you of is that RMHAM is a 501c3 public charity. The stuff that we do here at RMHAM University, our microwave network and all of our repeaters are supported by donations from everybody. So if you wish to make a contribution, please do so at rmham.org, or if you just catch any of the purple shirts at any of our events, that is always a place where you can talk to us and make a contribution if you wish. The other important thing to remember is that HamCon is coming up next October, the 23rd to the 26th. It'll be in Grand Junction. So we're hoping that our friends from Utah and the surrounding states, as well, of course, of Colorado, will attend that. We are still looking for presentations. So we'll accept presentations until a month before HamCon, so in September. But we are publishing a proceedings. So if you actually want your paper to be published in the proceedings, we need that by the end of August. So again, rmham.org is the place to go, and there'll be a link to follow to submit an abstract for HamCon. So the talks at HamCon is always one of the highlights. So please, if you have something that you wish to contribute, please do so at that link. We will provide feedback on your proposal promptly, so you don't have to wait till the end of the summer. But the sooner you get that in, the better it is for us to actually put together the schedule. We've got room for about 60 forums, so there's still plenty of slots left. The other very important announcement is that we will have another Swap Fest this summer. It is on Sunday, August the 24th, which would have been the DRC Hamfest, but because that got canceled, RMHAM decided to step up and instead have another Swap Fest in August, in addition to the one that we will have next February. So please visit rmham.org. The link is open to sign up for tables and more information. So the venue is the same. It's the Adams County Fairground on Sunday, the 24th. But it's just a different group that is actually running it this year. Anything else that I forgot? Thank you very much, and we'll hand it over to Mike Langhenry.
All right. Morning, everyone, both in the classroom and online. My name's Mike Langhenry. I am a communications technician, RF engineer, and a tower dude, both teaching and working on towers, a lot of time on towers. I'm an amateur extra, but I'm kind of not a real great ham. Most of my operating is out of my backpack, out of my truck. I don't have a home station. I very, very rarely, like once a year, operate anything even remotely close to HF. Don't own an HF radio, so I'm working on it. But yeah, very little HF. So most of the photos in here that you're going to see, a lot of the stuff that I'm going to talk about, is more applicable to sites. If If you make your home site look more like a radio site, you'll be in real good shape. The downside is it's going to cost a lot more money, though. I'm also a Motorola R56 certified installer. We'll talk a little bit about R56, what that is, what all that entails. But I did go through the certification class and did that last summer. Did end up getting that certification, so it's something pretty big in the two-way communications world. Today, we'll talk about grounding versus bonding. What are the two? A lot of times those terms are used interchangeably, but they do mean different things. And then why it's important, some of the critical differences between the two and why we want to apply grounding, good grounding and bonding practices in our shacks. Lightning, what it is, and the impact that it has on our radio equipment. I'm going to talk about R56 standards, kind of what it is, how it applies to communication sites, and how we can apply some of those recommendations or guidelines in our home shacks as we're either improving or building those systems at home. Entrance panels, it's kind of the key point with a home shack is where everything comes from the outside to the inside, protecting everything at that boundary so you're not getting electricity, power, static in or out through your house, keeping things where it belongs. And then the last point that I'll talk about is LPUs, SPDs, MOV, SAD, all the acronyms that are used in lightning protection devices. So with that, why do we bother with grounding, bonding? Anybody in the room? Couple of things. Yeah. Even bigger, even more important than that, safety's the big one. Safety is the main reason that we mess with bonding, grounding. It's also there to improve the reliability being how that device, how that thing performs to the manufacturer's design, and availability. You know, we hit that button on our radio, we expect that repeater is going to come back and do its thing. If we don't have sufficient lightning protection in there, if we don't have good grounding, good bonding, the chances of losing that equipment going down, are much higher. So by applying good practices, good grounding practices, good electrical bonding, meeting all applicable codes and standards, we can increase the reliability of that equipment, less frequent site trips, which I always like, and increase the availability. So you hit that button, you get that talk permit tone on push to talk, and everything just works. Best way to have things. So both grounding and bonding are required for electrical safety. Grounding and bonding fall under NEC, NFPA, National Fire Protection Association, UL, Underwriters Laboratories. They're the ones that test all this equipment, things like power strips, to make sure that when you plug it in, it's actually going to do what it says it's going to do, that it's not just going to catch fire, that it's actually providing the electrical protection that it says it's going to provide. As well as OSHA standards. OSHA falls in more with workplace safety, using grounded extension cords that have a GFCI, so that in the event of, if you're working in an area that's maybe exposed to water outside, if you're using power tools in an area that may lead to a ground fault, that you have that circuit protection in place. The grounding has to be in place for that GFCI to work. GFCIs are looking at a potential between the supply and the return to ground, between that hot conductor and that neutral conductor. If it detects anything going to ground, taking an alternate path, that circuit opens, protecting the user of that equipment. So grounding, we're providing an electrical return path back to Earth. This is a conductor that does not, during typical operation, carry any power. It is there for safety. If something's rubbing against, if you got a wire that's rubbing against the inside of a cabinet and wears through that insulation, electricity's always going to go to ground. Always. You want to provide a safe, controlled manner for it to get there, not take alternative paths like through your body. It can be dangerous, it can be uncomfortable, and bottom line is it's really just not safe. How we accomplish grounding is using tools like ground rods. I bet outside of almost every one of your houses, you've got a ground rod driven, probably near your service panel, that's connected to your electrical breaker box. That is providing the safety, that single point of connection of safety into your house. On tower sites, we don't always have the best grounds. Depends on the dirt, depends on the environment. We may use chem rods, ground rings, increasing the surface area of that ground. Older houses have the metal water piping, the copper pipe that comes in from outside. They use that as their as the ground. It's a very good quality electrical ground that goes all the way into the earth, below the frost line, meets all the electrical specifications. But as NEC has tightened up the guidelines, home builders are getting away from using copper water piping to supply the ground, and they're using an intentional conductor like a ground rod for that. Correct. An UFR ground is a type of ground that is connected to the rebar and the metallic elements of a concrete foundation. So it's less things that can go wrong, but it's not a foolproof method. There are still some caveats with that, and there are there's a handful more regulations that you have to deal with when you do apply that UFR ground in place. But it does work. This is not an all-exhaustive list of ground types. A lot of different like mesh type materials that can be laid down in the earth to provide a better to improve the ground of certain soil conditions. Contrasting grounding to bonding. Bonding is where we're making electrical connections, metal component to metal component, through the chain all the way back to ground, to a common potential. It's preventing voltage differences between metallic components, which reduces the risk of electric shock. So if you think of all the metal pieces that you have in your house, things like doors, door frames, windowsills, appliances, TVs, anything that's connected to an electrical supply, all needs to be bonded, provide that safety, that insulation, that alternative path for electrical ground to keep that device safe. There's always going to be a single neutral bond in an electrical system. You're only ever going to have one electrical bond. In a residence, in a building, that single electrical bond is at the service disconnect. Wherever your main breaker panel is, that's where neutral is tied to ground. Or the disconnect on the outside of the building. If you have a generator, and that transfer switch cuts over when you lose utility power, there's also a relay in there that's connecting that ground to neutral. It opens the neutral to ground on your service disconnect side. It's disconnecting all of those elements, keeping that one ground to neutral connection in place. Anybody have like kind of questionable wiring in their house? There's a number 8 screw that's holding on ring terminals that are crimped to Romex. That is those couple of wires coming off on the left there. We're going to 600 watt halogen tubes each. There's a lot of power, and I have no idea what a number 6, number 8 screw is rated for, but yeah, I got rid of that fire hazard. Yeah, it's real scary. I don't know how my house didn't catch fire. And this is after having 2 panel fires. So yeah, I'm kind of surprised that house is still standing. So grounds are a very good thing to have. If that neutral started to rub through, Rubbed through the electrical tape insulation on there. On my old condo, the dimmer switch for the ceiling fan in my living room just had electrical tape over the hot connection. Wires were just twisted together, no wire nut or anything, just using electrical tape on there. So if anything happened, that shorts out to ground. That provides that alternative path, that safe path, controlled path back to Earth, which allows that breaker to trip, allows the breakers, the other safety devices in that circuit to do its job. Telecom service entrances might have their own ground rods. Because it's a separate system, they're not, your telephone system isn't directly linked to your mains utility power. They can exist on separate ground systems. They should be. They're not always. This is a piece of equipment from an old job. And as I was working in here, cleaning up all the wiring, this is a 6-axis motion control system. We had a whole bunch of electronics in there. Those 2 motor drives on that door, those 2 big ones, are 240 volt for big motors. As I was in there cleaning everything up, rewiring stuff, as I drug my arm against the chassis of that enclosure, felt like I got into cactus. I just felt tingly, pokey on my arms. I didn't think much of it, like it didn't feel like I was getting electrocuted. As I'm going through there, like, still, I just itchy, feels weird. I don't know what's going on, man. This cabinet must be haunted or something. And I'm going through there, and I start getting to the power inputs. On this right side photo on the right side, there's those 9 IEC power inputs. But one of them had the ground and the neutral reversed. So the chassis of that equipment enclosure was carrying current. And it was that current, it was that voltage difference that I was feeling on my arm. It wasn't much. There was enough other things plugged into that cabinet that gave it a mostly good enough ground path that I wasn't getting like electrocuted, shocked from it, but it was enough that I could feel it. Something was not right there. That same shop for those 240 volt circuits, we had a shade tree electrician that worked for us, and he decided to rewire some of the outlets in the shop to 240. But instead of doing things the right way and putting in like a 240 volt plug, just used the same 120 volt plug, because we just know that plug is 240 and it's special, and we didn't want to replace outlets or anything. Everybody that worked there that summer kind of knew what was going on, but our part-time machinist comes in, plugs in the heat gun to heat shrink some cables for us. Turns out a 120 volt heat gun will work really good for a really short period of time on 240. It was an exciting place. A lot of stories from that job. But yeah, so that safety aspect of having a chassis ground that's not carrying electricity, it's important. Had we not had all of those cable entries, all those ground connections, there's a chance that power from those motor drivers could have gone through me, the way I was working on that with those other inputs. This is a drawing off of a communications site. This one in particular is a public safety. It's carrying police, fire, medical. All these bold lines here on this drawing, these are all 3/0 big ground wire. You can see there's a ring around the tower structure itself to the top towards the gate. There's a second ring goes around the structure, that building, both the building and the generator. The generator is tied to that shelter ground ring. The shelter itself is tied into that shelter ground ring. The fence surrounding the perimeter of all that equipment is also tied into the ground ring. tower ground ring and the shack guard ring, ground ring, are bonded, CAD welded, exothermic weld in two places. So there's a good solid connection between those two ground rings of big, heavy, solid wire. Those two rings, that amount of copper that's buried in the ground is what provides the solid, reliable, quality earth ground. That specific site is a B2, classified as a B2 site. That site, all the grounds in there have to have 5 ohms or less to ground. So it has to be a very good, very high quality electrical connection to ground. As your ground resistance, the natural resistance of that ground increases, the more grounds or the different types of grounds you need to have, things like chem rods or additional length cable.
I have an interesting comment based on that picture that you were showing right there.
Mm-hmm.
That is actually installed incorrectly.
It absolutely is installed incorrectly.
So where that number 210 comes through and that 3/0 twisted copper goes through the bottom, those should use bonding lugs to tie those to the metal chassis. Anytime you put that ground conductor through a metal choke, you stop the lightning potential dead at that point. If it isn't at the same potential as the box,
right,
that box turns into a choke.
Correct. Yes. The other thing that's wrong with this, we've got copper to aluminum, dissimilar metals. I scraped it, and it was not copper. Yes. This one that comes out in front and then goes down and across, that's the one that ties the building steel, the skid that building is set on into that ground system. That green wire that comes down and goes into the wall, that's the one that goes up to the main ground bus inside that everything is tied to. So that wire is carrying everything that's coming back in from inside the shelter back to ground. That is the main crimp for that entire shack right there. That wire that's going up is the one that goes into the service entrance. It's the one that's providing that neutral to ground bond in the service panel. Other things that tie in to our ground ring that's all bonded together, piping, raceways. If you've got plumbing that comes in for propane, natural gas, diesel from an exterior storage tank, all that needs to be tied in. Conduits, HVAC units, all needs to be tied in. Fence posts, part of the R56 standard, 40-foot maximum span. Corner posts, the gates need to be bonded to the corner posts. Everything gets grounded. Everything goes to ground. Yep, little jumpers to the gates. Ideally, they're S-shaped rather than U-shaped so that as that gate flexes, there's less wear and tear on that copper wire inside that conductor. Welding cable works well, but there is a size and style of wire that is intended to be used for that. Sold as a kit specifically for fence post grounding. Right. Yes, now it's a lot easier because there are just kits out there. R56 is a much more accepted standard. Clicking buttons here that I don't mean to click. Now that R56 is a much more widely known, industry accepted standard, companies have stepped up and developed kits and pieces that make complying with that standard far easier.
Lucky enough to have aluminum wire, what do you do?
It's pretty much tear it out. If you've got aluminum wire, you can use a corrosion inhibitor like Noalox to help prevent some of that galvanic corrosion, that dissimilar metal. Yes, should. Whether that happens or not, I don't see it very often. So, but yes, you should use that. There should be a goo under that crimp lug because of those dissimilar metals. And that'll help prevent that, helps prevent that corrosion. So grounding and bonding in a vehicle. We're looking at a motorcycle here on the left. It's got a subframe. It's got a little bonding jumper that connects to the battery. The earth in a vehicle, can't really tie it to earth. So we call earth on that vehicle typically the chassis. There's that bonding jumper that connects the negative lug typically of the battery to that chassis. That lug is what's carrying the return current for everything that's chassis grounded in that vehicle. Positive ground vehicles do exist. They're pretty rare. Don't see them a whole lot. Military vehicles and some heavy equipment still uses a positive ground, but don't see it very often. Question?
Yeah, I had a question. Kind of on your other slide, you'd mentioned some of the different standards and the low impedance that you've got to measure. Are you going to go into how you do some of these measurements? It's one thing to do it when you do it from a greenfield install, but
Right.
To go back to a site to find out. I mean, do you have to recertify these that hey, it still meets the standard? And with the Megarine, and are you going to talk a little about that at some point?
A little bit, yeah.
Okay, thanks.
Yeah, a little bit. Not going to get too in-depth in it. The equipment to do that is expensive. Most people don't have access to that. Some people do. Not everyone's that lucky. Because in a vehicle, because all of those systems in there are DC systems, DC is a lot safer. We don't require that additional separate neutral conductor because you're not going to get shocked from DC. Some of the electric vehicles now, yes. I'm specifically talking about 12-volt systems that are prevalent in conventional vehicles and the 12-volt system that's running lights and accessories in an electric vehicle. But yes, the EV drivetrains they do present an arc flash hazard as well as an electric shock hazard because of that increased voltage. But in most of the vehicle systems that especially anything we're installing a radio into, 12 volts, it's not going to hurt you. Some vehicles may have additional grounding straps between different components, like the engine, doors, tailgates, as well as any upfits that are put on that vehicle. Ambulances have a separate ground between the ambulance upfit and that frame. Campers, slide-in campers should also have an additional bonding between the frame and the camper itself. Snowmobiles are kind of an odd one. They're batteryless system, so the engine has the generator in it. It's that engine to chassis bond that's serving as that earth ground. But pretty much everything on there, all the power on there comes from the engine when it's running. So they're kind of unique vehicles. Most of the accessories that are added to those machines plug into the wiring harness, and the wire in that harness is your main ground because it's a different electrical system than most other vehicles. It doesn't have a battery as part of it. Anybody have trailers? Anybody had issues with trailers and maybe some lights not working? Trailers are terrible. The wiring on them is awful. It is done as cheap as you can go. Some trailers I've seen, they just take a single wire, string it all the way front to back. Every light just ties into that wire. They tie it in with Scotch locks that are insulation displacement. They bite into and through the insulation, tears up the wire in there as that trailer's bounced down the road. That wire flexes. It's going to break at the weakest point, which is at that connector. Just cheap. They're done very poorly. When you start getting arcs in an electrical system, it's creating a lot of RF noise. It may interfere with radios. If you have one light that's flickering, check that light, check that fixture. A lot of times it's a little pigtail with a ring terminal on it. Screw drives through that ring terminal that provides that frame ground for that fixture. Clean up any corrosion under that screw where it's making that electrical connection to the chassis. Seen those fail, seen wires pull out. If it's one light or one circuit, check that lamp, check that fixture, check that circuit. If all of the lights start flickering on different circuits, both breaks, your marker lights, everything kind of starts flickering on and off, check your ground. You don't have a good ground connection between the truck and the trailer because the truck's frame is tied to ground, the trailer's frame is tied to ground, your electrical ground connection is going through the hitch. It's not intended to be a current carrying conductor. As that hitch moves around, as it's bounced down the road, it's making and breaking that connection. You got grease, dirt, grit in there. That's what makes those lights flicker. Another easy way to check this is if you plug in your trailer before you totally hitch up, none of your lights work, you don't have a ground connection there. Take a voltmeter, poke between the vehicle and the trailer with it disconnected from the truck. See if you got voltage there. You're usually going to have some voltage, half a volt or so, just because of the resistance of the ground wire between the truck and the trailer. A little bit of voltage is normal. If you got like 11, 12 volts across that, you don't have a ground connection. If you have a generator that you use and you set that outside of the trailer, especially if it's a camper, make that bond between the trailer and the generator. If something shorts out in the trailer, you may accidentally energize the frame of the trailer unknowingly to the generator because that you don't have a ground connection between the trailer and the generator. The circuit breaker is not going to open. So we always want to keep that ground. We always want to keep a bond between the portable equipment that we're using and the generator itself. It is important, but it's often pretty much always overlooked. Even on construction sites that fall under OSHA, it's pretty rare to see a generator that's properly grounded, properly bonded. RF grounding. How is RF grounding different from electrical grounding? An RF ground is dedicated ground to handle RF signals. It's a low impedance path to ground versus a low resistance path to ground. Allows those RF currents to flow back to a common point. In many cases, it can increase your antenna efficiency, especially if it's an antenna that needs a ground plane. Quarter wave antennas are a good example of this. They have to have that return path to ground. Without that energy is still going to find a way back to ground. If you don't control it, it's going to take a path to ground that's unintentional, may cause issues. It might go through telephone wiring, might go through your electrical system wiring, might go through your stereo and you hear it over the speaker on your computer. It's going to find a path to ground, so do what you can to control where that RF current is going. Reduces interference because you're controlling that path versus that energy taking an unintended path through other wiring. RF ground might be shared with other systems ground. Take this NMO mount drilled into the roof of a truck. Talked about the earth, that ground of a vehicle being the chassis. That RF ground is also using the chassis as its return path to earth. So they may be shared. It might also be independent. If you got an antenna sitting out in the field, HF antenna, you lay out those radials, provide that RF ground. It's an independent ground from the power system ground. Any power system grounds that you have, keep those ground cables short to prevent that RF from illuminating those cables and those cables becoming RF grounds. You guys ever seen the little Part 15 sticker on a TV or a radio? It says, this device may not cause harmful interference. Part 15 device is an unintentional radiator. But Part 2, this device must accept any interference received, including interference that may cause undesired operation. So that undesired operation, we may be causing that unintentionally because we have a poor RF ground in our system. 9:06, you want to take a break? Take a question?
Yeah, we can just do a quick comment and take a break if you want. It's one thing I wanted to point out for people watching along at home. What Mike said about the low impedance or low Z ground path, that actually matters a lot for power systems too, because if you think about what a ground fault or a lightning strike is, that has a really, really sharp rise time to it, and that means it's actually a high frequency signal. So if your grounding system has a lot of impedance, if your wire is really long or undersized, that basically makes it an inductor, and that means that it's not going to be able to divert that energy safely away to ground as quickly as you might like it to. So that's what Maxwell was talking about here earlier with having to bond those grounding wires to the boxes and all the metal conduits. All that is designed just to get that volt, get that fold out of there as fast as possible.
No sharp bends.
8-inch minimum bend radius on for R56 standards. All your bends are nice, radiused, sweeps to ground. Yeah, for sure.
Lightning does not go around corners.
Right. It also doesn't like to go back up. There's a couple of radio sites we'll be working on this summer where the ground comes off the coax, does a U, and then it's attached to the tower, like with a hose clamp, going upwards. So we're going to change some of that stuff around when we...
Lightning should always take the path of least, and will always take the path of least resistance. When you come off the coax, point that straight down and make sure that it continues straight down to the ground ring. If you go and put a loop in it, really nice, it's going to look pretty, but the lightning won't like it.
Right. Exactly. It had to travel how far? It's going to make that jump. Awesome. If we're good for next group of slides, we'll continue. Break? Yes? No? Cruise till 9:30. So, like Tristan was just saying, is lightning AC or DC? Yes, exactly. That is exactly my answer. It has characteristics of both. Lightning by nature is a static charge in the atmosphere between the clouds and the ground. The electrons during that strike, during the fractions of a second of that strike, are flowing in a single direction. Definition of direct current energy. However, just like Tristan was saying, because that discharge happens quick through several transient impulses, that rapid rise time, fall time, looks a lot like AC. That signal that's going up, crashing back down, comes back up, crashes back down. The low impedance signal mimics AC behavior. Lightning strike is just a large-scale static discharge event. Typically 100 to 300 megavolts, carrying about 30,000 amps. There's a lot of energy there. One of the classrooms that I teach in, dry up there. It's all vinyl flooring. Everything upstairs is plastic. You guys have seen that scene in Office Space where every time he goes for the doorknob and it draws that arc, zaps him, it hurts. Same thing happens there. That is what lightning is, just on a significantly smaller scale.
So I have a story of stupidity. I was trying to solder a new connection on the end of one of my HF antennas. And while I was trying to do that, I kept on getting zapped. And all it was is there was enough, it wasn't a lightning storm nearby, but there was just enough static in the air that it threw that little 2-3 millimeter spark.
Yep.
Come back tomorrow. Don't do it today.
Right. Right. There are ionizers that you can get to help with desk size static control. Using ground straps is another good method for that. But yeah, some days it's just better to shut things down, disconnect things, and come back when you don't have that condition. So I don't want to talk a whole lot about lightning safety, but I think since we are talking about lightning, it's important to bring up some safety topics. If you're outside working on around equipment and a storm rolls in, if you're outside, seek shelter. Avoid being the tallest object. Avoid being around tall objects. It's just down the hill from Almagre. There's a whole lot of nothing up there, well above tree line, and lightning storms up there roll in pretty quick. And if you're caught out there, it's a pretty long ways back down to safety. So I'm not sure who put that up, whether it was Forest Service, BLM, but there's a lightning shelter in place, just a big, well-grounded shelter. Protect anyone that may be recreating up there from a thunderstorm. If you're on a tower and a thunderstorm rolls in, get off that tower as fast as you can. Things get real weird up on a tower in a lightning storm. You'll see a flash of light from the strike off in your peripheral vision, and then like that ladder that you're climbing, there's a little gap between the J-bolt that's holding the ladder to the tower, and you see an arc in there. Tower starts making funny snap, crackle, pop noises. It's quite unpleasant to be on a tower site in a lightning storm. If you're on, say, a 1,500-foot tower, it's going to be 45-minute climb back down. Best thing you can do is to hug that tower. The reason that we want to stay close to that tower is to minimize the step potential. When you're hanging on that tower, your hands are attached, your feet are at the base of that, you are another high resistance element in that tower structure. Most of that current is going to go through the low impedance path to ground through that metal structure. Some of that is going to go through your body. By staying closer to that tower, you're increasing that contact, you're decreasing your resistance relative to that tower. Less chance that you're going to get zapped that way. It's still not a place I would recommend being. Radio site shelters are pretty safe. It's usually a pretty solid, reliable ground connection. A lot of times it's like a metal roof, so you've got some protection there. Buildings are usually built pretty well, withstand the elements. Just be aware that if you're inside of there, there's a lot of electronics, a lot of wires, a lot of cables running around. If that site takes a strike, if that tower takes a strike, there may be high transient voltages on some of that wiring. So make sure that you stay clear of any devices, any wiring, receptacles, conduit, EMT, anything that's in that, telephones, pretty much anything that's in there. Try and keep as much space from anything as possible.
My mother said stay away from mirrors. They're dangerous too.
Yeah. Some shelters, a truck may actually be a safer option.
Mirrors don't attract lightning.
Another joke. So why should I ground anything at all if it just attracts the lightning, right? How does lightning choose what to hit? Or if it's going to come to a certain area, what's more likely to get struck versus not? Is there any rhyme or reason behind this, or is it a crapshoot? How does that work?
Lowest impedance path to ground is generally what's going to get hit. That old saying that lightning never strikes the same place twice is absolutely false. But yeah, there's some like rolling ball theories. There's a lot of research that's happening right now on like how lightning's actually conducted, how lightning forms, how the streamers form from the ground up, and then they make that connection. This little device that I got right here is a lightning detector. It's one of the things I carry in my truck when I'm out on tower sites, carry it with me if I'm out on a motorcycle. Starts beeping, starts flashing lights when it detects lightning nearby. This thing's just a little radio receiver. It's just looking for that wideband RF pulse from that high rise time, that fast fall time of a lightning strike. I'm not totally sure how it works, but it'll actually tell you distance away. Tell you the number of strikes and a distance away. It's actually pretty accurate. I'm not sure what kind of magic it's doing inside of there to get that. If you're on a field operation, lower the antennas if possible. If you've got towers, portable antennas, masts, drop those down. Don't let them be the tallest thing around. Disconnect them. Again, if possible, disconnect that equipment, preferably at the tower site rather than just yanking the coax off the radio. And then seek shelter. Get out of there, get off the top of that mountain. If you don't have shelter around, squat down, minimize your contact with the ground to prevent becoming that path to ground in the event of a lightning strike. Step potential in a nearby strike could energize the ground. So you want to keep you don't want a wide stance. You want to keep your feet kind of together because if there's a nearby strike, you could have enough of a voltage difference across the ground for electricity to cross between your feet. Same kind of situation that I was talking about on a tower when you get that lightning strike, that voltage potential may take that path through you rather than through that tower. That's called step potential. So with a direct strike, really as far as protecting equipment goes, good luck. Just trying to minimize the damage. Lightning is wild, natural phenomenon. You can do as much as you can to protect yourself, your equipment, from that strike, from that energy. There's still a lot of unknowns there. It's like you can only prevent so much from happening there. Tower structure, a lightning rod above the highest antenna will help prevent equipment damage. The idea is that that lightning rod will attract more lightning that will get struck more than your antenna will. If you have an antenna at the top, a DC grounded antenna that has electrical connections on the element of that antenna, helps to take that potential lightning strike through the antenna and then shunt it to the tower structure where it can be grounded and taken care of that way. And then hopefully tower itself is well grounded. Got a good ground connection at the base so that anything that gets hit on top goes through that tower and then is safely dissipated to ground instead of taking alternative unintended routes to ground through coax, through power cables, through your equipment. On buildings, lightning rods or air terminals help. They help dissipate some of that static charge, and then you're controlling that energy in the event of a direct strike. This photo that I got up here, it's a kind of new technology, starting to see them more, typically on data centers, hospitals, EOCs, dispatch facilities, high value, like multi-family residences are starting to put them up there. They're pretty expensive, but it's an active device its purpose is to improve the efficiency of the lightning rod, and it generates a small amount of energy to try and reduce the intensity of a strike by bleeding off some of that streamer emission charge. Not totally sure how they work. It's pretty new technology. I haven't found a whole lot of clear and concise evidence, but there is some testing from like certified labs that show that these things do actually work. Kind of interesting new technology out there. Basically what it's doing is reducing the standard deviation of the energy dissipated in strikes. So it's a more controlled energy discharge rather than kind of rolling the dice on whatever that lightning discharge is going to be. The cable used for lightning protection systems is often braided for surface area, increases the surface area, helps keep the cost low. You add a little bit more airspace in there that's not copper, but it's still like dollars per foot. It's pretty heavy, typically pure copper or has a zinc cladding or an aluminum cladding on it. Another reason for it being braided is if it is carrying the energy of a strike and the intense heat that's created in that strike tends to blow that wire apart. By being braided, it forms a mesh, blows apart, but then it'll collapse back down after that temperature has reduced after that strike. So that braid helps keep things all in one piece instead of just blowing apart completely. So these towers are, both of them are commercial towers, but this one on the left, that's a lightning rod that is installed on the top of that tower, 120 feet. We did end up installing a new antenna that did exceed that height, the height of that lightning rod, but it was a DC grounded antenna. It was a solid mast that was securely attached to the tower itself. And then this photo on the right, we've got a 16-foot antenna with about 18-foot lightning rod right next to it. So the idea is that lightning rod's going to take the brunt of that energy. That antenna is a custom-built antenna. It's got that parasitic element on it. It's also grounded at the base of that antenna. So there's some protection there as well if it does take a strike. I got some photos. One of them Willem brought in of a gas discharge tube inside of a polyphaser. This is from a amateur site in California, just outside of Santa Barbara. It was a most dramatic lightning storm they'd seen in at least 50 years out there that March. Repeater site stopped working. Sent a crew up there to take a look. This was the photo on the left is the first indication that something was going wrong. It was a big burn mark right next to a conduit outside. Once they got inside, they did their troubleshooting, realized that the polyphaser, that gas discharge tube inside of there did its job, but it was blown up. Solder was melted. They lost the power amplifier, but other radios at that station survived, which I thought was pretty incredible to take a lightning strike like that and still survive. This is one of those gas discharge tubes. This is one that Willem brought in recently. You want to talk about what was going on here? Yeah. Got an open circuit in there somewhere, and yeah, I probably shorted out.
You can kind of see just here, I'll put it down so you don't have to try. This is
Grab a microphone.
sorry. It's one of these alpha deltas, right? So here's a actual connector here, and this is the device. If you unscrew this, this is what it's supposed to look like. That one, you can actually see there's some arcing and melting on it. So I don't know that it actually took a direct strike, but it was pretty darn close. So didn't lose any radios, but basically the SWR on that antenna just went, completely off the scale. So clearly something bad happened.
Yeah, did its job. Those gas discharge tubes, they'll take and shunt quite a bit of energy. It's a fairly limited lifespan. It's not something that can continue to take those strikes and dissipate that energy over and over and over and over again. A couple of strikes and you start having failures with that, or it just blows apart completely. This one is a tower that I was on Monday and Tuesday. 160-foot freestanding tower, about an hour east of Oklahoma City. I was out there doing a round of tower classes. I showed up Monday morning. Everyone's kind of running around, panic mode, putting out fires. Radios are down, links are down. Don't know what's going on. The tower took a lightning strike that Saturday on the 19th. I was on site for a climbing class, 21st and 22nd. Ultimately, traced everything down. There were 2 damaged radios, sector radios on that tower, or 1 sector, 1 dish. 1 damaged lightning protection unit outside of the cabinet. Again, the MOV's devices in there did their job. They protected that camera from total destruction. Unalived 2 ports on that router that were working before and are no longer working, so red tagged those. Move those devices to other ports on that router. But ultimately, the tower grounding lightning rod up there did its job. It minimized the damage. You can see there's a lot of other radios up there. Most of them survived. Didn't have any major issues other than the 2 radios and that lightning protection unit for the camera, and then the ports on the router.
One of the things that we found back in the cellular days is we would put lightning rods on the top of the towers, but the high impedance bumps at every one of those connections of the tower going down created problems. So we actually ended up having to go and CAD weld that tower on the base plate, a jumper between each of the sections of the tower on a 180-foot tower. Yeah, that was a lot of fun.
Yeah.
But it solved the problem. It stopped things from getting blown up.
Right. That's one of the differences between R56 standards and NEC standards. EMT conduit per NEC is allowed to be that ground conductor. Per R56, you have to put those little jumpers in there because that set screw union between the two is not sufficient to meet R56 standards for grounding. So by putting a jumper between those tower sections, reduces that impedance bump, keeps that impedance low. Lightning wants to go to ground, the path of least resistance, going to take that path one way or the other.
What's that cable hanging off of the side of the tower?
That is the tagline that we were using to skate that radio down. That once we pulled the radio off that sector, smelled strongly of burned electrical components.
I would have just thrown it off by that time.
Yeah.
Everybody's wearing a hard hat, right?
Yes. They had several other sites around that area that had equipment issues. Some of them were just resetting equipment, bringing it back up again after it took that power bonk. There was some equipment that ended up being destroyed from that same storm. So they were kind of running around like crazy, dealing with equipment while I was there. Stuck around pretty late Monday night trying to take care of everything.
The other thing that you mentioned there, the unalived ports on the router, that has been, one of the banes of my life.
Right.
Is, all the radios and everything else is fine, but there's just a port on the router that just got blown up because they're basically 5-volt tolerant ports. And, even if the induced voltage is only 25 or 50 volts, it just blows up that transceiver, and
Right.
that port is no longer any good. I've also had that the NAND flash on the router becomes
Memory
unreliable
fries.
if it's been zapped a few times, and that's a
Yep.
very insidious problem that it works fine for 5-10 minutes and then starts misbehaving. So for the most part, if you've taken a good strike, maybe that's a good time to actually replace that router.
At some point, you got to make a judgment call on how many ports is too many bad ports. What else could be wrong with that device that you just haven't uncovered yet?
And please put a piece of tape over that port so that next time
Yes.
that I try to plug something in, I'm not
Yes.
tearing my hair out.
Mark it, change the name in the router. Yes, make it obvious that that port is no longer functional. So, does anybody have a switch that has like a ground position or a common position in it? Have maybe disconnect the cable from your radio to prevent any damage? Not a bad thing to do, but if you think about how far that lightning strike had to travel to reach your tower, even the distance from the tower to the ground really isn't that much. And if you just disconnect that coax from the radio and leave it hanging down on the ground, you're going to get a light show in your house. Hopefully you have a fire extinguisher handy. You're going to be putting out fires. Thunderstorm clouds form around 40,000 foot elevation. Even if you're 7,000 feet, it already had to travel well over a mile, several miles, to get to your tower. So jump in that gap of a disconnected coax or a coax switch like this Alpha Delta here. Yeah, don't trust a coax switch. You're just disconnecting your radio. It might save some of your equipment, but it's not going to protect your house from lightning damage. Indirect strikes are another cause of loss of equipment. It's a little bit easier to protect equipment from indirect strikes. There's less energy there, significantly less energy than a direct strike. There's less heat. Inductive coupling between that strike and typically the cabling going up the tower behaves like a wireless charger for your phone. That's how that energy is transferred from one place to another. Cables act like a big antenna or a secondary winding in a transformer. That sounds great. Take a break. 10 minutes, 15 minutes? 9:45. Catch you guys back here at 9:45. All right, guys, welcome back. Talked about indirect strikes, how they're easier to protect equipment from because there's less energy there. The inductive coupling between that arc itself and your equipment acts like a wireless charger, and the cables are typically where that power comes in from. The cables act like a big, long antenna in that tower. The energy is going to go somewhere. We want to protect it from getting into our equipment. So in this diagram, we've got a nearby lightning strike on the right with our radio tower, the feed line coming down that tower in red. When that arc happens, that red feed line acting like a big antenna. It's just picking up that energy that's induced by that electrical strike. So where's the current going in this diagram? It's either going up to your antenna, to the microwave radio or the camera that's up there, or it's going to go down into your shack, into your radio, potentially destroying some equipment. So how can we keep this induced current from damaging our equipment? Add some grounds. Most of the induced current is carried on the shield of a coax. We take that shield, we ground it near the antenna, slap a cable kit up there, tie that cable kit, good, solid, reliable ground to that tower. Tower is a low impedance path back to Earth. Keep that induced current that was coming up that antenna, hits the top of that, right back down to ground through the tower. That induced current that went downwards towards the base of the tower, give it an opportunity to hit a low impedance path to ground at the base of the tower through tower bus bar, tower ground bar. Where the coax goes from the tower, makes that stretch across the ice bridge, comes down the building and then into the building, we have another exterior ground bar, secondary grounding bonding bus. Try and keep that power, that energy outside of your building, away from your equipment. Inside is our main grounding bar, our primary bonding bar. That's where our polyphasers mount to. That is the primary connection of our lightning protection system. And that's where the center conductor is shielded to ground. Anything that comes in on that center conductor is shunted to ground through a polyphaser at the main ground bar. But bottom line, we're giving that energy a lower resistance path to ground than going into your radio and through that equipment. This coax grounding kit, these are relatively inexpensive. They strip back some of the insulation on your coax, just cut it back to the shield, snap that ground kit on there, weather seal it, and then tie that cable down to end. This one, photo on the right, is up about 120 feet. It's for electric meter reading antenna up there. Antenna's 2-3 foot off the post of that tower leg. Got a ground kit just before the connector that goes to the antenna. That conductor goes nice big ground radius, nice big bend radius straight to ground on that tower through that beam clamp right by my foot. So again, anything that comes in at that antenna, just shunting it to ground, to that low impedance ground of the tower itself. As that coax comes down the tower, comes down that cable ladder, we have another ground kit just above that tower ground bus. All those cables, all those coax lines have another ground kit on them. It's tied to ground, provides that energy that came down that tower, place to go back to ground. Your coax shield is grounded here, tied into that tower ground ring from that tower ground bar, or TGB as we call it. From there, that coax goes under the ice bridge, hits the exterior grounding bar, EGB, or secondary bonding bar at the cable bulkhead panel. So there's yet another ground kit on that coax there, shunts that energy back into ground, into that grounding ring on there. The secondary bonding bar or exterior ground bar is a extension of the main ground bar. Some grounding kits, ground bus kits, have conductors that actually penetrate through the wall of the building. So your exterior and interior, you don't have a wire connection between them, but an actual threaded, hard electrical connection between the two. So your coax shield's grounded here, tied into the shelter's ground ring. And then on the inside, once those coax pops through the bulkhead connectors into the building, hits your main ground bar, or your primary bonding bar. So your lightning protection units, your polyphasers, these guys that are protecting your equipment, the center conductor of your equipment to ground, these are all mounted inside on that main ground bar. Again, it's a low impedance path to ground through number 2 ground cable. It's usually should be CAD welded to the shelter ground ring. Halo system, interior perimeter bonding bar connects to this main grounding bar on the inside of the building. Before I move on, why it has 2 names, main ground bar, MGB, or primary bonding bar, PBB. Industry is moving to calling it a PBB, primary bonding bar, to align with international naming standards. A lot of places, a lot of technicians will still call it a main ground bus, exterior ground bus, rather than a bonding bar. These 2 photos here, this one on the right, you can see a halo system wire going around all of these conductors, all these coaxes coming in from the doghouse on the roof of this building. That particular building is a dispatch center, a sheriff's office dispatch center. So all the polyphasers that are on the coax are connected to ground through that halo system, which then connects to that main ground bar. Main ground bar goes back through the building steel down to earth. Photo on the left is the data center, data room of a fire station. I didn't have a whole lot in there yet. They're still moving in, but when I was installing the radio equipment, the antennas for the fire radio repeaters, bolted that polyphaser right to that ground bar. They got some other equipment tied to it as well. And then that big 2-aught cable coming down ties back into that building ground, provides everything in that rack with lightning protection, grounding. So that halo system, or IPBB, internal perimeter bonding bus, it's not a continuous loop, except in the case of AT&T. We want a single point ground. So in the opposite corner of where that cable entry is, where that main ground bus, that primary bonding bar is gap. Minimum 4-inch gap between the ends of those halo wires. The reason for that, everything goes back to that primary point and then goes down. Yeah. Question?
By having one of these ends that's connected, does that not just create like a stub where you have the potential for some current to go towards but not be able to leave?
Not intended to be a stub like a resonant antenna, if that's what you're...
Does it behave like one, though?
No, everything goes back to that single point ground. That halo system is in place to attach parts, pieces, other pieces of metal that need to be bonded, things like fans for ventilation, light fixtures tie to that, door frames tie to that, ventilation louvers, keeps the critters out, but those ventilation louvers, any screens, grates over that ventilation, all need to tie to ground and be bonded to that ground system. They can do that through this IPBB, this internal perimeter bonding bus. We can also shield Ethernet cables. Should shield Ethernet cables. Anything that's going up to like a remote radio head or a microwave radio or a camera on that tower. Some of the new, I think it was Yaesu, their new low power like one of their radios has a remote head on it. The power amplifier, exciter, everything is actually on the tower. So your RF connection is nice and short. You have an Ethernet connection, a data connection between the control head and the radio itself. So you have one of those, you'll want to protect that equipment as it comes into your house. Use one of these little surge suppressors here. Ubiquiti makes these. A couple other companies make them. Come in a handful of different flavors. Thank you, Ubiquiti, for never attaching the cover to the body of the device. I wish I could buy a 10-pack of these because I drop them off the tower regularly. Super frustrating. So make sure you got a good hand on that and then stash it somewhere where it's not going to fall off the tower because it's not attached to the device that is attached to the tower. One of these has some Ethernet ports in it. Go on the correct camera here. We've got some Ethernet ports in here, Ethernet in and out. Makes it easy to just use a jumper cable to go from the radio to the surge suppressor, and then from the surge suppressor back down that tower. Maintain that lightning protection. There's a screw with a ground stud in here. That goes to something on that tower that is electrically grounded. Then once you've made your two Ethernet connections, hopefully you snap that cover back in place. You don't have to ask the ground guys to find one. And yeah, fairly weather resistant, fairly durable products. And these are honestly not all that expensive. Easy way to protect your equipment on the tower. Differential signaling, the way that Ethernet communication travels along those lines, is more resistant to common mode noise. So those impulses that are put on that wire by lightning, by electrical noise, because of that differential signaling on Ethernet cabling, it's more resistant to that. Ethernet cabling is also usually shorter than coax runs. We're not going to be running coax all the way up a 2,000-foot tower. I'm sorry, not going to be running Ethernet up a 2,000-foot tower, where we will do that with coax for larger broadcast facilities. Those taller towers that are more prevalent out east, not going to be running Ethernet all the way up there. Probably going to run fiber up there. So shorter runs than coax, is less that needs to be protected because those runs are just inherently shorter than coax typically is. So microwave radios, cameras, power injectors, any other equipment, remote radio heads, they're more sensitive to ESD and then that current on all 8 wires that are in that Cat5 cable than, say, an antenna. It's a relatively passive device, which is why it's important to protect those devices on your tower. Cabling that we're using makes a difference too. We want to use FTP or shielded cable, and then only ground the side that's towards the ground. Give any induced current that gets onto that shield only goes one way, and that one way is back down to ground. Don't shield it. Don't connect that shield on both sides of that Ethernet connector. Inside the shack, once that coax comes in, run it to another transtector inside. This one is a little bit different. It's got punch-down terminals in there. It does require a little bit more tool It's not as easy to replace as the Ubiquiti one that has the Ethernet terminals on it. But up here we've got the gas discharge tube. We've got a couple of fuses. They're literally just wires on the PCB. I got some bridge rectifiers and then MOVs for surge suppression. A big ground lug on the side. This would tie to our main ground bus. Number 6 wire on this to be R56 compliant. A couple of grommets on the bottom to run your cable in and out, keeps them weather tight, and then mechanically strain release that cable. So these get kind of pricey. Some of the, like to buy them brand new, I want to say they're in the $150 to $200 range. But for the cost of the equipment that's typically getting plugged into them, surge suppressors are usually pretty cheap. Easier way to go, send data up on glass. We don't have conductors. There's no electrical conducting happening. You send fiber light up there, don't have to deal with as much lightning protection. Like you can't shield fiber because there's nothing to shield. You still have to run Ethernet or power up there, but you can run a switch, a powered switch that will break off from that switch with short jumper cables to those devices. Only have to protect one DC connection from the shack going out to that switch. That switch is going to provide that PoE power for all your radios up on a tower. So starting to see that happen more often. More companies are running less cable up the tower. They just run 5 gig fiber up to a switch, and then from that switch out to all those radios. How we doing on time? Take 5. Continue.
Just one other comment is, I love Raspberry Pis to death. They are just very useful for all kinds of things.
Super delicate.
The problem is all of those GPIO pins basically allows you to attach an antenna directly to the pins on the processor.
Yep.
So they are super, super sensitive to anything that you try to control. Now, as long as you put that Raspberry Pi in a metal case,
right.
The RF that is typically in that environment is, fairly well behaved. But as soon as you try to connect anything to those GPIO pins, watch out. You are going to have all kinds of problems. And so, for example, it may seem like a great idea to use one of those one-wire temperature sensors to actually measure the temperature on the heat shield of your, transmitter or whatever. But, you've got a 2-3 foot antenna that you've just attached to that processor. And, soon as that thing, whether it's lightning or just RF in the environment,
right.
Do not expect that Pi to last very long.
Yeah, there's advantages and disadvantages to those low-cost microcontrollers. And protection and isolation is often the first thing that's stripped off of low-cost devices. Most people aren't going to put a Raspberry Pi on a 12,000-foot mountain where it's exposed to that lightning quite as often as some of us around here tend to do. Another story, Willem, that you brought up is this SCE. You want to tell us a little bit about this one?
My favorite story in the whole world.
Grab a microphone.
So, this here is just a replica. I just couldn't have one. We're going to make this part of our AV so that at some point in time, when something goes wrong, I can tell Dave my SCE talks. And basically, the story is that SCE is the condition equipment So in the Apollo days, was digital very much in its infancy. So how all of the telemetry from the spacecraft went back down to the ground was through this big box was called SCE, Signal Conditioning Equipment. And basically all of those signals came into this one piece of hardware that would then multiplex that signals in one of a gazillion ways to actually then send that down as a single carrier down that they could then decode for all of their telemetry. Well, what happened with Apollo 12 is about 40 seconds off the pad, the spacecraft got hit by lightning, and this knocked all of the fuel cells in the command module offline. Now, it turns out that the systems that was actually running the stage 1 booster that was running at the time was completely independent of what they had in the command module, and that kept on running functioning correctly, but all of the telemetry that was coming from the command module per se, the SCE was basically, the voltage to the SCE dropped below the critical threshold, and so everything in the mission control, all of the telemetry went away and everything just got scrambled. And there was this steely-eyed missile man called John Aaron that remembered seeing this particular behavior. And they actually planned for this. So on the panel down here on the lower right-hand side, there was this switch that would allow the SCE to either run on the main bus, or you could switch it to auxiliary, and it would run on an auxiliary bus, and it was specifically designed to be able to run at a lower voltage. And so the famous words is flight try SCE to aux, and it so happens that one of the astronauts actually knew what the hell that meant. He flipped the switch, and all of the telemetry came back. And so, you know, saved the U.S. taxpayer billions and billions of dollars, because in the end, Apollo 12 landed on the moon instead of aborting, you know, 40 seconds into the mission as a result of that lightning strike. So the bottom line is, you know, even people like NASA that have thrown lots and lots and lots of money at lightning protection, you know, sometimes you just get bad luck and you get struck by lightning, and if you properly account for what could happen as a result, you could save favorite stories to tell. And so you can buy these from this company called Concorde System, Concorde Aerospace. I think they're like $60 a piece, but you know.
Pretty cool piece of history.
What can I say?
Yeah, pretty cool piece of history there.
So I'm going to
Take 10? We can take 10 if you want. Okay. It was just a good break between modules, so thought I'd give you guys the opportunity. So I've mentioned a few times now, what is R56? R56 this, R56 that. R56 is standards and guidelines for communication sites. Motorola pioneered this a number of years ago. It's a reference that now became an industry accepted, is no longer a proprietary standard. Other operations, other organizations have feedback into it. So other organizations are ANSI, ASTM, IEEE, ISO also provides feedback for it. NEC, NFPA, UL, Underwriters Laboratories, as well as FCC and FAA. They all provide feedback to and typically go for adherence to the R56 standard. provides mandatory installation requirements to meet R56 standard, as well as recommendations for enhanced protection. Things that you can do, things that installers can do to improve the level of lightning protection, safety, reliability, and availability of the equipment that's being protected. There's some differences between R56 and NEC standards. Mentioned earlier that grounding jumpers per NEC, if you're using metal conduit, you don't need additional jumpers. The set screw provides enough electrical connection to function as a ground according to the NEC. R56, they want to see a separate external jumper around those unions between those pieces of EMT. That's something that a lot of places don't install. Costs more money, it's more copper, but it does, in order to meet R56 standards, it does have to have those jumpers over the conduit. R56 is a 4-day training course. Certification covers all of the things that go into R56. First couple of chapters of that get into site design, so it's a civil, structural, mechanical requirements, guidelines of a communications facility. Covers some of the electrical work, supporting equipment, pad mount transformers, the generators, how that skid's mounted, how fuel tanks are mounted. Covers some of the warning signage that needs to be in place on the tower. Everything from like safety equipment, fire suppression, even down to the amount of lighting in between the aisles of the racks of equipment that are in a facility has an R56 guideline for it. It's heavy on the grounding and bonding aspects, location and quality of the grounds that are in place on communication sites, things like ground bars, ground rods, test wells. This photo on the right here is a test well of that underground grounding system of the communication site. You can take a clamp-on resistance meter, reach down into the web of spiders and clamp onto that ground and check to see how well that ground leg is performing. Is there anything, corrosion, something that damaged or destroyed that ground leg that would then impede the ability of that ground system to function, do its job, and meet the requirements of R56.
So the bar the ground that's in there is actually connected to the true ground. You're
Correct.
using that as a reference to see how well your other grounds work, or does it actually connect to this ground well?
So it's all one piece. It's just a loop that's pulled up into that test well. Current is put onto that wire around from that inductive loop. A known current measures the voltage drop time across that. With that, it can calculate the resistance of or the quality of that ground.
And it's just the DC resistance?
I believe it's testing AC because it's looking for that impedance. Yeah. Interesting thing to note is that any NEC, NFPA, UL, government, federal, or local codes will prevail over R56. If R56 says everything needs to have this level of ground, and a specific local code says do not do this, that, or the other thing, that local ground prevails over R56. So in addition to knowing what R56 is, you need to know the local jurisdiction as well as the federal NEC requirements for specific aspects of grounding and lightning protection. Makes that job a little bit of a struggle.
That evaluation just on the grounding that I have in my shack. How and I don't have the $5,000 piece of test equipment, how
Yeah, you got to call someone with that $5,000 piece of test equipment. The clamp-on ammeters, resistance meters, about $1,500. Sweet. Is that one of the 4-wire ones or just the clamp-on ones? Ah, sweet. Yeah, I didn't know we had that available. Those are good tools to have. Real good tools to have. Different communication sites all have different requirements and different levels of those requirements that need to be met. This photo on the left here, this Tough Shed, it's a meter station. It's got a 120 volt circuit coming into it. It's counting ticks on a water pump, and then it periodically relays that back out to a master station. Really not doing a whole lot. That site is what's classified as a type A site. It's not highly exposed to lightning. There's no tower directly attached to it, although if you know that site, there kind of is. Typically small, remote sites that don't have a whole lot of equipment. If that site goes down, it's not a big deal. It's not like a fire department no longer has radio communications if we lose this little wellhead test site. It's considered a type A site. Grounding requirements for a type A site is 25 ohms to ground. So it's pretty generous. Doesn't have to be as good of a system as a public safety crime site does. A site that has a tower, mission critical installation, or a large installation, something like a data center, would classify as a type B site, the 10 ohm requirement to ground. So every ground in that facility has to have 10 ohms or less to a quality ground connection. Next step from that is a critical site. Things like an occupied building with a tower, a dispatch center that's got a tower adjacent to it, or a tower with a shelter that contains critical equipment. So if there's a microwave shot from police dispatch to this tower is where the zone control or the heart of that public safety radio system is that type B2 site, which has a 5 ohm requirement to ground. So significantly increased quality of that ground. Typically, they're prime or master sites, the ones with zone controllers. Loss of that site would result in significant degradation or complete loss of communications, which is why they're held to a higher standard than something that if it goes down, it's not a big deal. So differences in the size, differences in the requirements of those sites change the grounding requirements, change the physical requirements of the shelter and of the building itself.
So that one that you've got there on the right, there is no ground there. That's sitting on solid granite.
On rock, yeah.
So how do you solve that? What do you do?
Bring ground cables down to a place where you have a reliable ground.
There isn't one.
With enough of them to a suitable location.
So when this site was constructed in 1993, there's about 20 18 by 18 copper pads that are buried in the foundation of the building, sitting on the bedrock with bentonite on top of them before they poured the concrete. And then after that, there is 3/4 inch copper water pipe flattened and run down the side of the mountain, buried under the dirt. There is no ground on the top of that mountain.
That low quality ground there.
But I've also been in that building probably twice when it was hit by lightning. I know that building gets hit by lightning all the time.
Regularly.
And we have never lost a radio in there due to lightning.
Right.
And I've had equipment in that building since 1993.
Since it was built. Yep. Yeah. Yep.
I would also comment that I've been to a few ham repeater sites that the building on the left looks like the Taj Mahal compared to them.
Yes. Yes, I can think of a couple of those. Yep.
Mention no names, but follow my eyes.
Sweet. Yeah, those are nice. Bluetooth, and yeah, they run that about $1,500 range. Not something that most people would just have in their toolkit. It's not like a multimeter. It's definitely doing a lot more power. Very unique tool to measure very specific things. The best way to measure ground is with a 4-point Wenner test. Known current is generated by the tester. It's typically a large box, and then electrodes are placed many feet apart. A known current is generated by that tester, looking at the drop-in potential measured over significant distance. Do a little bit of math, V equals IR, and that resistance is able to be calculated of the ohms per cubic meter of dirt in that area. On a typical evaluation of a communication site, they'll take 4 or 5 of those readings around that communication site to see what kind of dirt they're working with, what the conductivity of that soil is, to figure out whether we need to do copper mesh, copper pipes all the way down the mountain, or whether we can shove a couple ground rods in and then have a sufficient ground system for the type of shelter, type of tower that we're building on that mountaintop.
Are there any time of year or weather fluctuations that affect this?
Yes.
Okay.
Yeah. Whether it's middle of summer, it's been dry, or whether it's winter and you've got water on the ground, the amount of salts in that soil may change seasonally, does affect that. Chem rods will typically need to be serviced, refilled, checked to make sure that that electrolyte is in there at the proper amount and conductivity to keep that soil at a condition where that ground is able to perform.
So do you have to do this at a particular time of year, or can you assume a worst-case scenario when you're making these tests?
Typically, it's done like during the worst case, tested, make sure it's functional, and then as the year progresses, things should just get better from that worst case. But it is done. A couple of companies that I know that do it, try to get out there annually or every other year, to ensure that the ground system is functional, doing what it should be doing. Let's say this tester on the right is a clamp-on resistance tester. It's used to locate poor-performing ground rods, specific components of that ground system that may not be in as good a condition as it was when it was installed. Able to identify open ground conductors. So if there's a crimp lug or a CAD weld that was done incorrectly, it can be checked with a tool like that clamp-on ground tester. R56 also sets standards for internal grounding. There are all sorts of bonding bars out there. RBB is a rack bonding bar, a bar that's going up and down the length of that rack, which then ties back into another ground bar, goes across the building, ties into that main ground bar, which then reaches ground. NBB, or a network bonding bar, common if you've got a stack of switches. They're all the same depth. They're all in the same rack. You can put a network bonding bar on the back of those, take that bonding bar to your rack bonding bar. Rack bonding bar goes up and then to ground through there. There are specifications for suspended or drop ceilings like what we've got in here. How do you install a ground in a facility that has a drop ceiling? Also raised floors. Typical in a data center. How do you ground a facility with a raised floor access underneath that floor panel for equipment that's not bolted to like to a poured concrete floor. Requirements for cable trays, the supporting structure that's handling those cables, keeping them neat, tidy. There are regulations for the distance between a transmitting conductor and a receiving conductor. You want to keep 4 inches between those conductors, and then 2 inches between non-transmitting conductors. So don't just take that bundle of cables, smash it all together, pull a zip tie over it, because you're going to lose some reliability. If a lightning strike, that high impulse does get onto that ground conductor, it may arc over the insulation and then get into other equipment if everything's tied close together. And then electrical noise can be coupled from one conductor to another if everything's just smashed together. So some of these towers that all of the cables are just tied together in one leg, it's easy to run things up there, but kind of doing a disservice by having everything tied that close together. Public safety sites, they're going to run everything up their own cable supports all the way up the tower. So trying to keep that physical separation between transmitting and other coax lines going up the tower.
Say something more about the network bonding bar. How is that different than just grounding all of the equipment that are switches?
It's easier. It's less wire between everything. So you just put a bus bar on the back of all those pieces of equipment where everything is nicely in line, and then you have one wire that goes from that bus bar up. It's less components to fail when you have a solid bar connecting that equipment versus several discrete wires that go to a...
Is this bolted directly onto the chassis, or is this something that you have cables terminating to?
It goes to the chassis, like a ground stud on the back of the chassis. If they're all the same brand, model, everything's going to line up real nice. They sell bonding bars specifically for that application. Just snaps on, everything's rack mounted, height, width, where everything is. Snap that on and ground all your equipment much easier that way.
To forget when you want to try to pull the switch out and it won't come.
Yes, yeah. Make sure everything's disconnected, including that little ground lug on the back. Yes. It's also specifications for operator and dispatch positions. How do you ground a facility like this where we've got a bunch of different tables, there's laptops out on those tables? How could we apply a grounding technique, bonding technique to bring all of these different computers that are all, I'm sure, at different voltages to the same common potential to minimize any ESD or safety hazards that would be presented by a difference in voltage of that equipment. Power systems is another heavy aspect of R56. Utility power, 100 amp, 120, 240 volt service is considered the minimum, which I thought was kind of a lot for a radio site. I know a lot of the ones that we have in the RM ham network are nowhere close to 100 amp service. A lot of them that I can think of that barely even have 120 volt service. Generators, solar systems, each of these things have to have a service disconnect for each power source. The utility power coming in has a main disconnect. Generator has to have a main disconnect. If there's a solar array, that solar system has to have a main disconnect. You got to be able to isolate those different power systems. UPSs, there's a battery or a rectifier system in the facility. That needs to have a main disconnect as well. This one was for another power company. That battery array is one of two in that building. There's another exactly like it on the other side of this rectifier in the middle. But one of these panels right in the middle is right-hand bank disconnect and your left-hand bank disconnect. So there's an easy one single switch to cut that entire battery string out of being able to provide power to the equipment microwave and RF equipment in that shelter.
The RMM University on solar systems about all of the dangers of dealing with high voltage solar systems. So be careful with those.
Yes, and it's hard to turn off the sun when things start going sideways. Yeah. Let's do one more slide, and then we got a good break point. So one of the last things of the R56 standard has to do with equipment layout, spacing, placement inside the rack, how far things are from the walls, space between the aisles, egress routes, ventilation clearances. This photo here is a site that is being decommissioned in the next couple of months, but they want to keep it online until the new system is installed and operational. So they went in, pulled all the bolts off the racks, pulled all the support off the top of the racks, the seismic supports, shoved those racks up against the wall. Kept everything connected. They're still working. They're still online. But if you need to go in there and take a look at something, or if you got to yank one of those heavy radios out, you can't get to it from both sides because everything's been shoved up against the wall. This is an image off my thermal camera. When they shoved everything up against the wall, they shoved it up against the wall with a thermostat on it. So there's a toasty warm PDU that's top corner of it, sitting about 84 degrees. Right next to the thermostat that's controlling that mini split on the back. So yeah, pop the door open and it is frigid cold inside of there because that PDU is just sitting there cranking out heat. Thermostat thinks it's nice and toasty warm in there, so that mini split's just running on max cool all day long. So maintaining clearances to HVAC equipment is important for not just the life of the equipment, keeping the temperature control of that equipment, but also the longevity of the HVAC equipment. That pump is just running 24/7, trying to keep that thermostat cool, and that PDU is just keeping that thermostat warm. With that, let's take 10, 15. What's on the books here? 10:45. See you guys in 12 minutes. some equipment with me. Some apps on the phone that do that pretty well too, for lightning strike identification. Cool, welcome back everyone. So just talked about R56 and all these standards for communication sites, how to lay out a shack, how to ground, bond everything in there. That's great for building a communication site. How does that relate to us as hams? Taking all this kind of best practices and then make your shack R56 compliant. First thing you want to do is take out a second mortgage. You're going to need a bunch of test equipment. You're going to need a lot of copper. There's going to be a lot of heavy yellow equipment, tearing up the yard, digging up the garden. Make sure you call 811 before you do that. You're installing ground rings, copper bus bars inside and outside your service entrance. For a house, it's kind of unrealistic. You've got what you've got. Treat it like a type A site, maybe a type B, but it's like your house isn't a critical communications facility, and to increase the grounding, safety, reliability, and performance to an R56 standard that a communications site is built to is really, really just unrealistic in cost, in time, and just plain feasibility. You're going to be redoing major components of your house to achieve that standard. So if you are driving additional ground rods in, make sure to call 811. Have that utility locate done before you drive anything in or trench any coax in. Make sure you know where the fiber, coax, power, water, gas lines, where any of that stuff is. You don't want to get tangled up in that. Realistically, your existing house ground, probably good enough. Using the electrical ground in your house system, for the most part, it's going to do its job. It's rated to carry that fault current of the circuit that it's on. A lot of times you just don't need to add more. Tower grounding, however, is not a bad idea. It's more likely to get struck by lightning. It's more likely to see that streamer formation during the early stages of a lightning strike. Good tower ground is also going to enhance your RF ground, which will enhance the performance of the antenna systems that you have on there. It's a good idea. It's also a good idea to follow good workmanship practices. So keeping everything neat, clean, tidy. I was getting on guys about tying nice, good, clean, well-dressed knots in ropes class last week. As a professional, it makes you look better to the customer. As coworkers, you're holding yourselves to better, higher standards by tying those nice, clean knots. Workmanship with any electrical grounding system is kind of the same way. Next person that buys your house, if they got to deal with a rat's nest, not going to be real happy with you. It's going to be difficult to figure out where things are, where things go. Following good workmanship practices, labeling things, putting tags on circuit breakers, at bare minimum, writing which breaker goes to which outlet or which light is a good thing to have. And then most importantly is following NEC and local guidelines when you're adding ground rods, and then how to connect those back to your system. Any changes to the electrical system will typically need to be done, or at least signed off by an electrician, by a real life electrician, not a shade tree electrician. As far as entrance panels go, kf7p.com. I'm not affiliated with him. I haven't bought anything from him yet. But if I'm buying an entrance panel, it's probably going to be through him. It's a one-stop shop. He sells everything that you need for the enclosure itself, grounding bar, grounding plate, copper ground plate in there, polyphasers, grommets, terminal strips. If you've got RF that goes in, polyphasers for that. If you've got rotor controllers that you need to protect, going from the rotator on your tower into the controller in your shack. This photo on the right in the top corner of that is a rotor controller surge protective device. So many sizes, many options available from him, and everything that I've seen looks very high quality. Ones on the right are polyphasers, yes. Yeah, Polyphaser, Transtector, there's a couple other brands that make those devices. But downside to the KF7P stuff, because he's running good quality equipment, brand name, surge protectors, it's going to cost you. Depending on the configuration, it could get pretty expensive. Yes.
Yeah, it's a lot cheaper than buying a new radio.
Yes.
Main thing to watch out for those polyphasers is they are DC isolated. So if you're trying to just make sure that your connectors are working, the polyphasers will actually be isolate the two sides DC, whereas the alpha deltas, which are the ones shown there, do not. So just keep a few more hairs.
Yes. Yeah, the alpha deltas are nice because they do give you that easy access to the gas discharge tube. But
is the DC blocking a good or a bad thing? Does that affect the level of protection at all?
for troubleshooting, makes it easy when you can easily pop that out, take a visual inspection of it. You see black marks like this one, something's probably wrong with it. If it looks like a good, clean, nice, everything's readable. Just doing an inspection on that stuff, it's nice to have the access to it. You can do that if you have a vector network analyzer. Do a transmission measurement through there. That'll tell you if it's good or bad or not.
Just be aware when you're doing stuff like GPS that it probably needs voltage to the antenna.
Right.
So you need to know that the device that you've connected to it is not trying to pass current up the line. So
right.
Just be aware of
They
it.
do sell DC pass and DC block. Spec that lightning protection for the signals that are going over it, frequencies as well. Not all of these devices are rated for the same frequency band. Some of them are wider frequency band, higher frequency bands than some of the other ones on here are. Next step down from the KF7P stuff is like a broadband cable entrance enclosure. Fairly low cost. It does require more parts. You're not going to be able to source all of the parts that you need from, you probably get most of them from Amazon, but I don't know if I'd trust them all from Amazon. It's a little bit more of a DIY solution. If you're a tinkerer, you're interested in building your own, or if you have specific requirements, one of these broadband entrance enclosures might make more sense for your application. Go into it with a plan. Have an idea of how many radios you're connecting, how many coax lines you're bringing out there, how many telephone, Ethernet, fiber, rotator lines are going out there. Size your system for what you've got now, plus future expansion. Any changes that you make, if you run out of ports, if you run out of space inside of there, now you have the additional cost of a second entrance panel. DX Engineering sells an entrance panel kit. Comes with a few of the pieces that you'll need, but they're basically just a broadband cable entrance box. Get it right from DX Engineering. Neat thing with those, they do have pre-punched holes or knockouts to go into conduit mounting points, and they are fairly weather and UV resistant. They're designed for outdoor installation to be install once and not have to look at it, not have to deal with it again for a number of years. Going even cheaper from that, again, more DIY solutions, a window panel. I wouldn't recommend using that for a permanent install. You get a couple of these bulkhead connectors, drill some holes through a 2x4, and make yourself a bulkhead pass through that way. There's no provisions for grounding or attaching polyphasers on a system like that, unless you build it that way. The window may also no longer be weather tight if it's still open. There may be a gap where the seal doesn't fully close, lets water in. Now you've got water inside that windowsill, potentially damaging your house. However, if you're on a budget, that may be an acceptable solution, so long as it's not a permanent solution. Some of the questions online was if you've got a 2-story house, all your equipment's on the top story, how do you ground that? Again, are we building a B2 type critical communications facility, or is a type 1 acceptable? Type 1's probably acceptable. I would recommend just using the grounding that you have in your electrical system already. Grounding the tower to a good, might be worth looking into some lightning protection, lightning rods on the house, and then grounding the tower to that, because that tower is going to have a lot more exposure to lightning. Make sure that tower's got a good ground on it. But really, the protection in the house that's existing is probably sufficient for a second-story building. Getting back to keeping things neat, clean. Don't make your shack look like this. Go into it with a plan. Anything that's decommissioned or not being used, take it out. If you don't take it out, if you're leaving it for future expansion, tag it so that the next person knows you remember a year later that coax isn't actually connected. Anything that comes into the house, even if it's unterminated, should have a surge arrestor on it. It should have that polyphaser on the end of it. Best practice to put a 50 ohm, just a little dummy load on there to keep everything grounded out and just basically cap off that end. So SPDs, LPUs, what are those? SPD is a surge protective device. It's a parallel connected device in line with your each phase of your ground system, as well as the neutral. So you've got phase to phase, phase to ground, and neutral to ground protection in there. In the normal operating state, these SPDs present a high impedance to ground. However, when the voltage increases beyond their designed limits, they very quickly switch over to become a low impedance path to ground during that surge event. Limits the surge voltages by automatically clamping that current to ground when that voltage exceeds its design intent. It's required equipment for all communication sites to meet R56. Pretty much everything needs to have an SPD on it. Alarm wiring, AC, DC power inputs, any control signaling that comes in, telephone, coax, video. If you run an analog CCTV, that needs to be protected. If you're on an IP CCTV, that also needs to be protected as it comes into the building. Tower lighting is another one. A lot of times the tower light controller itself has some surge protection in it, but it's often not enough for some of the tower installations. Manufacturer doesn't know exactly what type of tower and type of ground that those lighting controllers are being installed in. So you'll often need additional grounding on the tower lighting system.
Mike, a question from Zoom.
Mm-hmm.
Even though your ground system around your house is adequately grounded, it can often be long enough to be an antenna picking up noise from wall warts and appliances, which can put noise back into your radio receiver.
Right.
How can you mitigate a lot of that without compromising electrical and lightning safety?
Ferrite chokes help. Pull wall warts out. Other sources of interference are things like CFLs, fluorescent tubes. The ballast in there sprays out all kinds of RF noise. Cheap LED drivers, grow lights if you're next to one of those houses. A lot of things, some of it may be under your control, others may not be under your control. So, yeah, solar inverters are another. The MPPT controllers, pulse width modulation, as that current is toggling on and off, does create fairly significant RF noise on there.
What I found in my camper, the worst offender was I have a 12 volt to 5 volt converter, and it was just putting out everything from DC to daylight.
Right. Yeah, sometimes you got to do some investigation as far as what is actually causing that problem. Last year at Field Day, we had some issues with noise coming from, I believe it was a laptop power supply off that generator. So start killing circuits, kill your whole house circuit, run your equipment off battery, see if you still have that noise level. If it's still there, it's probably not much you're going to be able to do about it, coming from a neighbor's house, something else in the area. If it is improved when you kill your main breaker, start turning circuits on and see where that noise pops up again. Try and hunt down exactly where that noise is coming from, and then replace the component, add ferrites to reduce some of that RF noise, essentially an RF choke on that, on those wires, those antennas.
So the ferrites go on the coax, or on?
Ferrites go on the power leads, those little lumps that are on cables. Those are there to reduce some of that RF interference. So surges, power surges, they occur during transient events, things like lightning strikes. When power goes out, the switching from the utility, generator firing up, generator transfer switch closing, opening of inductive circuits or coils, like the ballasts in the fluorescent tube fixtures. When that circuit is turned off, there's a large inductive kickback on that that can create a transient ESD event. And then ESD events in general, capable of generating several thousand volts of electricity just in static electricity. So again, unused lines that are terminated inside the building need to have a surge protective device installed and be terminated with a 50 ohm load. Some of the acronyms, there's a whole bunch of acronyms when it comes to SPDs and LPUs, surge protective devices, lightning protection units. SAD is a silicone avalanche diode. It's a very fast response, can only handle a couple hundred volts. So it's going to arrest that, it's going to shunt that energy to ground fast, but it can't arrest a significant amount of voltage. So the MOVs come in, metal oxide varistors. It's a slower response. Slower on the terms of milliseconds, but it can handle thousands of volts. So those big lightning strikes, those adjacent lightning strikes, that can arrest the energy that's induced on those lines from that. Once, yes. I've also had issues with power strips. It's the cheap power strips running on a generator. We just keep them plugged in in the trailer, and then as the generator is started, stopped, started, stopped, started, stopped, started, stopped. There's enough transients on that startup and shutdown of the generator that starts to break down those MOVs. When those MOVs fail, they fail short. When they fail short, it makes a whole lot of smoke, whole lot of sparks, bunch of noise inside the trailer, and makes the trailer smell funny for a couple of days. GDT is the gas discharge tube. These are what you'll find in these polyphasers. They can handle a couple of surges, but usually not repeated surges. They're pretty good. They're fairly inexpensive. It's a finite lifespan on those. They do need to be replaced periodically. The other one that's in our surge protective devices is a TCO, or thermal cutoff. It's very slow. very, very slow type of protection. It's also called a self-resetting fuse or a thermal fuse. Because those MOVs fail short, by putting a thermal cutoff in series with that MOV, once that MOV opens and fails, that thermal cutoff will open, preventing that device from just shorting to ground perpetually. So there's some safeties built into that to prevent that device from catching fire in the event of a short circuit, internal short circuit from that lightning protection.
Any particular reason why you're actually terminating those unused lines with a 50 ohm load and not just shorting them?
Just providing a path to ground. Why it's not a short, I don't know. Don't have an answer for that one. It's a good question. Well, you've already got a good path to ground through the on the shield, and then a 50 ohm path to ground from the shield to conductor. Yeah, I don't know. That's a good question. It's a really good question. R56 manual, they do recommend terminating with a specifically called out with a 50 ohm load. Does anybody have a surge arrestor on their electrical panel? A couple guys do. Awesome. Okay, gotcha. Yeah, my house is kind of old. Got a lot of issues with it, so don't have the new code. Not up to that yet. They're fairly inexpensive to install. They do need to be installed at the panel to be functional. And then per R56, does yours go through a circuit breaker?
Actually is in the format of a circuit breaker, so basically slots on as same size as a 2-pole breaker, and then it has a neutral pigtail.
Gotcha.
Actually, I don't think it even has that since I have a plug-on neutral panel, so I think it just clicks in once, and then that protects the feed coming to that panel.
Right. Does it have a? But does